Hello and welcome to lesson number 4 in Unit 6, Solving Problems with Quadratics in our Grade 10 Academic Math class. So far in this unit we've looked at how different forms of the quadratic relations can be used to determine pieces of information that might be asked in a word problem. That was lesson number 1. Lesson number 2 and 3 were optimization problems, problems that involved a quadratic where you were being asked to find the vertex. It wouldn't always say find the vertex, but it would require you to find the vertex as part of this solution to the word problem. Today we're going to look at the first of 2 lessons on solving problems using factoring or the quadratic formula. So what you'll recognize here, hopefully, is that the difference between optimization and solving is a difference of tools, which just means that when you're being asked to find to answer a word problem with optimization, you're going to be looking for a vertex, which is going to require us to complete the square. If you're being asked to solve, then you are going to use one of these other 2 tools. You're going to either use factoring or the quadratic formula. So let's jump right in. The introduction, of course, is just a recall of what the quadratic formula is, which says given 0 equals ax squared plus bx plus c, which is just sort of a fancy way of saying all of the terms have to be on the same side. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That's one of the tools we're going to use. The other is factoring. Obviously, factoring is sort of a little more general skill. Let's see if we're going to use it. Example 1. The hypotenuse of a right angled triangle is 15 centimeters. The sum of the other 2 sides is 21 centimeters. Find the lengths of the other 2 sides. Okay, so now would be a good time to hit pause and have a look at our let statements. So this question is asking us to find the lengths of the other 2 sides of our triangle, which means that we're going to be looking for a and b, or x and y. I've chosen a and b here. So let a and b represent the lengths of the legs of the triangle in centimeters. That's our let statement. There we have just a little diagram for us. As before, we now need to start building some equations. So let's build ourselves a couple of equations. The first equation is telling us something about the relationship between the legs of the triangle. And that is that the 2 legs, when added together, give us 21. So that's our first equation. In terms of our degree, this happens to be a degree 1 equation in that the largest exponent on any of our variables is 1. The second equation that we're going to create is specific to right angle triangles. A right angle triangle has a very special tool that you can use when you're working with it, and that's called the Pythagorean Theorem. So the Pythagorean Theorem is a squared plus b squared equals c squared. But in this case, they have told us that our hypotenuse is 15. That's right in the beginning of the question. So we now have 2 equations here. As before, we are always going to be substituting the linear equation into the quadratic. So always linear into quadratic. I'm going to make a little reorganization here of the first equation so that we can substitute it in. So we have a plus b equals 21. Let's manipulate that a little bit. Let's get a equal to 21 minus b. We're going to call this equation number 3. And like I said, I want to make a little note here for us. Only once per lesson I'll do this, but I want to remind us that we always sub linear into quadratic. And linear, of course, is a degree 1 equation, and a quadratic will have a degree 2 of 2. And once I'm done writing this word, always sublinear into quadratic, important to remember. We'll see that this is actually a degree 2 equation here because we have the largest degree, or the largest exponent on any of our variables is a 2. So we are going to sub 3 into 2. That's where we start. So we're going to sub 3, which is a reorganized linear, into 2, which is our quadratic equation that we have built. Okay, so we are going to be replacing a. A will be replaced with 21 minus b, and that's all being squared, plus b squared equals, I'm going to go ahead and square 15. That's going to give me 225. And now I'm going to expand out. So this is actually, I'm not going to do a full, well, you know what, I will. I'll do a full rewrite on this particular step because it's 21 minus b squared, which means, which means 21 minus b times 21 minus b plus b squared equals 225. So now let's go expanding out. So we're going to start by doing 21 times 21. That's going to give us 441. Then we have minus 21b, minus 21b, and then plus b squared, plus b squared. So that's this b squared here. And then we have equals 225. So now we're going to simplify. I'm going to bring 225 over to the other side by subtracting 225 from both sides. So let's do sort of all in one step here. We have two b squareds that hang out. We have minus 42 b's, and then we have 441, and we're going to subtract 225 from it, and that's going to give us plus 216 equals 0. All right, so this is looking good so far. What we have here is a quadratic in standard form. We can use the quadratic formula. I'm going to start by common factoring 2 out of everything first to see if maybe we can, maybe there's something we can factor here. So we have 2, and then we'll be left with b squared minus 21b plus 108. And that's going to equal 0. Now I believe this is factorable. I think that you can get 108 by multiplying 9 and 12. So we are going to go about factoring this. If you're not sure, like if you're not great at factoring and you're just not sure how to begin, what you can do is you can use the discriminant here to tell you exactly whether or not you should try to factor or use the quadratic formula. In this case, I'm just telling you, but if you wanted to, you could go ahead and use the discriminant. So now we're going to jump in over here. I'm going to do a recopy step where I've got 2, and that's b squared minus 21b plus 108 equals 0. And now we're going to go ahead and factor that. So as I said, I believe 9 and 12 will work for us. So that'll be b minus 9 and b minus 12. If you're a little rusty on factoring, you can go back to Unit 3 and have a look at factoring of simple trinomials. That'll be hanging out there. And now we're going to set each of these factors equal to 0, since we're being asked to solve, which means find values for b that make the left side of the equation equal the right side. So we have b minus 9 equals 0. We transpose 9 to the negative 9 to the other side by adding 9 to both sides. And we transpose 12 to the other side, negative 12 to the other side of the equation by adding 12 to both sides. So we have two possible answers here. And again, that jives with what we know because, and again, you don't have to copy this part down, but you'd consider that this quadratic, if we were to graph it, if we didn't set it equal to 0, if we just kept an input and an output variable, you might have something like this that has a couple of different b values that are going to work for us. So this is entirely consistent. There's nothing weird about having two answers. This does, however, require us to consider that there are two possible solutions. So now we are going to, I'm running out of space, but I'm going to squish it in here somehow. So we are going to, we're going to find A. And remember, we have two different scenarios now for this. So A is equal to 21 minus b. So our first possibility is a is equal to 21 minus 9. And our second scenario is a equals 21 minus 12. What's interesting is that once you do this math, you realize that a will equal 12 or 9 respectively, which are matches for our, I guess sort of each value is equal to the other. So when you're using b equal to 9, it spits out a 12. When you're using b equal to 12, it's spitting out a 9. So those are our answers. And we're going to go write our therefore statement in this really nice wide open area over here. Therefore, the legs are 12 centimeters and 9 centimeters. Now I will say that had they not been equal to each other, so like this part over here, if this had spit out something different than 12 and 9 when you subbed in 9 and 12 respectively, there could possibly be questions where there are two sets of answers because we're dealing with a quadratic here, so there are possibly two sets of solutions. So don't be alarmed if that happens. It wasn't the case here. So this is our first example. I'm going to stop this one and then we're going to look at example 2 and then example 3. And then you can head off to do some homework. So I'll see you in part 2.